This is f of x. Now it's not single input anymore, and not single state. Gj of x, uj. And I'm looking for a transformation z equals t of x, right? And also transformation for the u. The u here was something like a function plus something in the new variable v. So u is alpha plus beta v. These can be function of x, that's fine. Right? I'm looking for transformation t to functions alpha and beta such that the dynamics in the new variable z dot is just az plus bv. Right? Any question about that? Okay, so these guys, things are what I'm looking for. Transformation, alpha and beta. Obviously, beta has to be non-zero, because otherwise you're transferring your system to a system that doesn't have control, right? If beta is zero, so just substituting u equals alpha, you will have no v. So the system is not controllable, you cannot do anything. So, okay. If I'm able to do that, do you agree that this is a good thing? Because I can work here, do whatever you like, stability, controllability, do ABQR, do whatever you like, do optimal control, and then here is the formula that will transfer your V to the U that you want, okay? To apply actually in your system.
Yeah, Professor, but this formula is going to be like algebraic formula?
Like this, exactly. I'm looking for T that will transfer it like this so that I can do here. And now I have my V as a function of time coming from the optimal control solution or whatever. These guys are just static functions, like x1 squared plus sine x2. Like magic, right? So here's an example, just to show you what I mean. Example, motivating example. So we have, here is a system, so x1 dot x2 dot equals a sine x2 and negative x1 squared. Okay? This is your f and this is your g, 0 and 1. And someone magically came and says, okay, please consider z equals, so this is z1 and z2, this is just x1, so this is the t of x, and this is whatever you have over there, a sine x2. And please consider your u to be, this guy is like x1 squared plus v divided by a cosine x2. Okay? Someone magically give you this transformation and feedback. So let's apply this here and see what we get. So we have z dot equals partial t, partial x, right? Times x dot. And actually here, this is t of x, right? z1, z2 equals t of x. And we should be able to invert it to get, x's from the z's and z's from the x's. So actually this is easy, x1 is just z1 and x2 is just, this is z2, so this is z2 over a sine inverse, right? Okay? If I just ever wanted it. So let's substitute here, partial t, partial x. What's partial t, partial x? So let's do that. So this is 1 and 0. Here it's 0 and a cosine x2, right? Times x dot, here is x dot. So this is x dot, is actually a sine x2. Here is u minus x1 squared, correct? The bottom. Okay, so u minus x1 squared from this guy is just v divided by a cosine x2. A sine x2 from this guy is just Z2, right? And you have your dynamics Z dot will be equal to 1 times this guy, so this is Z2 and 0 otherwise. 0 times this guy and a cosine times here, but there is a cosine down, so this is just V. So this is actually 0, 1, 0, 0, Z1, Z2 plus 0, 1, V. It's controllable canonical form with 0 eigenvalues, that's fine. I can adjust my eigenvalues by feedback of V, right? This is perfectly linear. Any question about that? So this magic transformation works, right? Our question today is, we want to see, can we always do that? Can we always find a transformation of feedback that renders our system linear form? And if yes, how can we do it? Okay? So far, the relation with differential geometry is none, right? There is no differential geometry in what I wrote so far, right? It's just nonlinear systems, that's fine. So we have, based on this discussion, we'll have the following definition. The system, this guy, maybe 2, is, the definition is for input state linearizability. So the system is input state linearizable if there exists transformation T in our language, because I want this guy to be differentiable, right? I want to differentiate it. There's partial T, partial X here, and I should be able to invert it to get the X back if I want. So, and the inverse should be also differentiable. What's the name of this map? Differentiable map, invertible, the smooth inverse is what? Diffeomorphism. So if there exists a diffeomorphism, right? That's okay, you can replace it with a smooth map with a smooth inverse. Diffeomorphism. But we are in a differential geometric course. So diffeomorphism T and these functions alpha, beta, right? Such that this transformation Z is T, blah blah, we have Z dot equals AZ plus B V. If you can find these guys, okay? This is, we will call the system input state linearizer. So in this lecture, we will work with single inputs. So all the details and everything can carry out, and you can find the details in either Isidori or Sastry book. I'll demonstrate here the things for single input. So we have X dot is, so X as an array, but I have just one input, so it's just one G. Okay? So just one input, and X can be anything, like 10, 20, I don't care. Okay, so I'm looking for, like I said, transformation Z equals Tx, U, it's not an array anymore, so this is alpha is a scalar, plus beta is also scalar, V. Here I have Z dot equals AZ plus B, it's just one column, right? Any question about that? So this is what I'm looking for. Okay, so let's apply the transformation, that's fine. So we have Z dot is partial T, partial X times X dot, and X dot from here is F plus GU, right? And actually also the U is alpha plus beta v. Okay? This should equal what? Should equal what? AZ plus, very good, plus B, V. Okay. And this equivalence should be valid irrespective of the value of your input V. You're going to get V from somewhere and apply it. It should be valid for all V. So in particular, if V is 0, it should be valid. So if V is 0, please get the things that are void of V. So I have partial T partial X here times F plus alpha G, right? Equals AZ from the right hand side. And simultaneously, also it should be valid for any V, in particular, say V equal 1. So you get something, and I'm gonna subtract it from here. So it's as if now I equated the terms that are void of V, now I'm gonna equate the terms that are coefficients of V. Okay? So let's equate the coefficients of V. So I have partial T partial X. This is times beta is a scalar. G. This is equal B. Right? So I'll move beta here actually, just to make it nicer. So 1 over beta. Okay? Without loss of generality, I will take A to be in the controllable canonical form. I mean, it doesn't matter, you take whatever A, because in linear systems, you can transform from any form to another by just a linear transformation. So I'll take A to be 0, 1, zeros, right? 0, 0, 1, zeros. This is the controllable canonical form, right? And here we have 1 here, but now we have the last row. Do you remember the last row representing what? Linear systems theory? Last row representing what in controllable canonical form?
Coefficients of the denominator of
The coefficients of the characteristic equation, which if you solve, you get the poles. So I will, again, without loss of generality, I'll take them all zeros. Why? Because I don't care. If the poles are all zeros, and I have a linear system at the end, I can move the poles wherever I want. It doesn't affect me at all. So I take this my A, and this indeed doesn't preclude generality at all. And the corresponding B for the controllable canonical form is just zeros, and the last element is 1. It's very easy to work with these guys because there are lots of zeros here. And let's do the equivalence. We just have two equations. This red and this blue-black kind of thing. So I will drive everything from here. Okay, these are two equations. So partial T, partial X. This is the Jacobian, right? So what's the first row? Do you know what's the first row? T, by the way, T is an array. It's T1 up to Tn. So the first row is all derivatives of T1. Then the second is all derivatives of T2 and so and so. So this is indeed nabla T1, nabla T2, and so and so. Right? And I will multiply by F plus alpha G. I can actually move the alpha G to the, that's okay, just leave it. This is equal to A times Z. My A is very nice. Zeros. And Z is just T1 of X, T2 of X, up to Tn of X, right? Any question about that? And the other set of equation is, let's see the other set of equations. Again, this is nabla T1, nabla T2, up to nabla Tn multiplied by G equal to 1 over beta times zeros and then 1. Okay? Any question about these two equations, please? Okay, straightforward. Then okay, now nabla T1 multiplied by F. What is this guy? Nabla T1 as a row multiplied by F as a column. What's that guy?
So the derivative of T1 in direction of that.
Yeah, this is the directional derivative. Nabla T dotted with F. And nabla T dotted with F in our language we call it the Lie derivative like this, right? And also the Lie derivative alpha G. That's right. Let's go and do this first. So nabla T1 times the G's. Nabla T1 times G, this is the Lie derivative T1 along G, okay? This is 0, correct? This guy, T2 is 0, all of them are zeros except the last one, LG, Tn is just 1 of beta, something that is unknown, but I know for sure that it must not be 0, right? That's it. Any question about that? So we're done with the greens, let's go here. So like I said, nabla T1 times F, this is the Lie derivative, plus nabla T1 times G, so this is the Lie derivative along G, but we just said that it's 0. So I have here something plus alpha G, but this is 0, okay? So LF T1 from the other side, right hand side here, is just T2, okay? And LF T2 is just T3, and so, until LF Tn. Okay, just wait a minute here. Because Tn is indeed not F only, it's F plus alpha G. We cancel G because over there it's 0. Now it's not 0, it's just 1 over beta, right? So I will just move this in the other side. So this is negative alpha Lg Tn. Okay? Plus 0. So, and this guy is simply LGTN is 1 over beta. So this is indeed negative alpha over beta. I got my 2n equations. These are 2n equations. What type of equations are these? What type of equations?